Hi everyone. In this mini lecture we are going to explore the quantum mechanical structure of the hydrogen atom. In other words, we're going to build up an answer to that question of what do atoms actually look like. Now let's take a second here to recap where we've been. We know that there's protons and neutrons and electrons which make up atoms, but we know that the simple sort of orbital model illustrated here doesn't capture the true nature of atoms. However, during a course of a number of experiments that we've talked about in previous lectures, we found out some of these quantum mechanical properties of these fundamental particles, electrons, protons, and neutrons that build up matter. Specifically, we've seen that these fundamental particles behave as both waves and particles. So this sort of duality, wave-particle duality, is a very strange quantum mechanical effect, and we know that it must play a role in any sort of theory that we build up. And so the good news here, when we are building up this theory, as I said before, all of the mathematical foundations that allow us to answer this question of what a hydrogen atom looks like are laid down in the theory of quantum mechanics. As we pointed out in this quote by Paul Dirac, again, one of the founding fathers of quantum theory. So quantum theory has all the answers. We want to know what atoms look like. We want to know their properties, how they behave. We need to turn to quantum theory. Okay, so first up, the types of descriptions that quantum theory gives us are a bit counterintuitive. And so when we talked about this sort of orbital structure of an atom and extended this to the Bohr model where we said, we've got these, concentric shells or stationary states, and we said how you can get different transitions between these states. We explored some, basic mathematical formula that allow us to predict this for certain subsets of atoms. These are nice in terms of helping us build some intuition for how atoms behave, and of course the basic building blocks of atoms, but these models are inherently insufficient and lack generality if we want to talk about atoms and molecules more generally. Okay, so quantum theory is going to change this concept of a simple orbit, and we're going to exchange it with a concept, what we call the orbital. All right, so we are going to come up with orbital descriptions of atoms and molecules. So let's see what I mean by that. Recall back to your high school physics class. If you were, say, trying to predict the path of a football, there's some simple equations that Newton gives us, one in particular here, F equals ma, that basically allows us to come up with a function that will predict the position of that football. So when you get to college, and you take college physics, you might frame this as a little differential equation here. However you say it, however you frame it, the result is the same. You're going to come up with some function, x of t in this place, that gives us the position of that football as a function of time, given some velocity, given some gravitational acceleration, etc., etc. So basically, you come up with a position function to describe what that football is going to do. Okay, so in a similar way, what quantum mechanics does is comes up with another mathematical function that describes the behavior of matter at this subatomic scale. So this function, rather than an x of t, is going to be a function that we call psi. We typically use the character psi to represent this mathematical description that quantum theory provides for us. So we're going to call it psi of x, and we call it a wave function. So remember wave. We already saw how electrons, and in fact all subatomic particles, and matter in general has both this wave and particle properties. So this quantum mechanical description, then, it's not surprising, the properties of waves are going to be playing a role. And in order to derive or arrive at this wave function, you need to turn to an equation. So rather than Newton's equation over here for classical motions at the large scales that we're all used to, for quantum mechanical problems, we're going to turn to another equation derived by a gentleman by the name of Schrodinger. in the early 1900s, and it's called Schrodinger's equation. So it's quite a mouthful. We'll abbreviate that SE. So Schrodinger's equation here, H psi equals E psi, mathematical function that if you solve, then you get this wave function solution. All right, now I've got some good news. This all seems rather abstract, but what we're going to do is explore this concept of a wave function without actually looking at any of the real mathematical details. Instead, we're going to focus on the results, right? Basically, how we interpret and understand these mathematical solutions. So first up, let's throw a definition out here. So the definition of an orbital, another name is, of course, the psi. We'll use psi to denote orbital or wave function. All of these terms are used interchangeably. So this definition says that orbitals are mathematical functions that satisfy this equation, Schrodinger's equation, and these functions describe this wave-particle nature of electrons, and they do this in a probabilistic way. And so the wave function, if you take the modulus squared of that wave function, you end up with a probability density. Okay, so basically you square this wave function, you get a probability density. Now we're going to spend some more time really looking at what is meant by a probability density, and we're going to look at specific probability densities, but the idea is relatively straightforward. It sounds complicated, but it's a relatively straightforward concept. Basically, this wave function, the square of this wave function, is going to tell us the probability of finding an electron at a given location in space around a nucleus. So around that nucleus. And so if you think of this as a nucleus centered somewhere here, right? Remember, we had to move away from an orbital description, okay? It's not going to be an orbit description to an orbital description. And so this orbital description replaces this well-defined orbit by a sort of spread out cloud of probability. I'm going to denote it by red here. And so that's like this whole sort of amorphous region where there's going to be a likelihood, a mathematically defined likelihood of finding that electron. And so all of these wave function descriptions that have this probabilistic interpretation, it's relatively abstract, but there's some basic principles that come out, right? And again, we're just following the mathematics here. So I'm going to ask you to just sort of bear with me, and we're going to make some sense of these facts later on as we do some further exploration. So the first fact, when you're looking at the solutions to Schrodinger equation, it turns out that there's actually an infinite number of these solutions, an infinite number of orbitals. In other words, there's an infinite number of different states in which we can find electrons around any given atom or nucleus. All right? And for each one of those orbital descriptions, there's a corresponding probability distribution. In other words, each one of these orbital solutions defines the probability of finding an electron in a given region of space around that atom or molecule. And each one of these orbital descriptions can be identified using a combination of three integers that we call quantum numbers. So if we're focusing in on atoms, and we're going to focus on hydrogen first, we can identify each one of these descriptions, psi, using just three numbers. And once you have that sort of three number identifier, then you have a well-defined orbital. And each one of these orbitals, it's important to remember, it has a mathematically defined shape and a probabilistically defined size. In other words, there's going to be a region of space where we're going to be more likely to find the electron, and that's going to have both a size dependence, depending on how far you are away from that nucleus, and what position you are from an angular perspective in relationship to that nucleus. Okay, that was a mouthful, right? And what I'm going to actually have you guys do is come back to that slide after we've gone through the next handful of videos. Okay, so that's just sort of a broad stroke of where we're heading, and at this point you're probably a little confused, And I'm going to draw you and point you right back to Richard Feynman's quote. Remember, if you're confused right now, that's absolutely understandable, right? Everything I said there is very strange, and quantum theory is very strange, and that's why Richard Feynman himself said that, no one really understands quantum theory. So we're going to go ahead and start from the very basics here. And we're going to start off by just labeling these orbitals. We're going to come up with essentially an addressing scheme so that we can talk about this infinite number of different solutions. So it turns out that this address, as I said, it consists of 3 numbers, right? And we're going to come up with a name for these. We're going to call these 3 numbers. Turns out they're integers. We're going to call them quantum numbers, and we've got special names for each one of them. We're going to denote one of these quantum numbers by an n, and we're going to call that one the principal quantum number. We've got another one. We're going to denote it L, and we're going to call that one the angular momentum quantum number. And then we've got a third one, M sub L, and we're going to call that the magnetic quantum number. And so what we're going to do in the following mini lecture is really explore in detail these quantum numbers. We're going to focus in, look at the relationships between these quantum numbers, and coming up with basically a very robust addressing scheme so that we can start to make sense of these different orbital solutions, these different orbital descriptions of atoms.